Transistor-transistor logic represents a logic family that utilizes bipolar junction transistors. In TTL, transistors handle both the logic function and the amplifying function, a departure from preceding resistor-transistor logic and diode transistor logic. TTL found broad use in various applications like computers, industrial controls, consumer electronics, and synthesizers following their introduction as integrated circuits by Sylvania Electric Products in 1963. The Texas Instruments 7400 series emerged as a popular choice for TTL integrated circuits, with multiple semiconductor companies engaging in their production. These TTL ICs encompassed a broad selection of logic gates, flip-flops, counters, and diverse circuits. Manufacturers offered variations of the original TTL circuit design to enhance speed or reduce power dissipation, facilitating design improvements. Initially available in ceramic and plastic dual inline packages, as well as flat pack form, some TTL chips are now also accessible in surface mount technology packages. Despite the advent of very large-scale integration CMOS integrated circuit microprocessors rendering multiple chip processors outdated, TTL devices continued to play a crucial role as glue logic facilitating communication amid more densely integrated components, ensuring TTL's enduring relevance in the realm of digital electronics. TTL was introduced in 1961 by James L. Buey of TRW as a suitable technology for integrated circuits. Originally known as transistor-coupled transistor logic, TCTL, the first commercial TTL devices were produced by Sylvania in 1963 as part of the Sylvania Universal High-Level Logic family. TTL gained widespread acceptance among electronic system designers with the introduction of Texas Instruments 5400 series ICs in 1964, followed by the more cost-effective 7400 series in 1966. Texas Instruments 7400 family quickly became an industry standard with compatible versions developed by various companies globally, including Motorola, AMD, and Fairchild. Typically, TTL chips integrated only a few hundred transistors each, ranging from basic logic gates to microprocessor bit slices. Apart from its technical advancements, TTL's affordability played a crucial role in enabling the widespread adoption of digital techniques for tasks previously handled using analog methods. TTL's significance extended beyond its technical capabilities, as seen in its application in groundbreaking devices like the Kenback 1, which utilized TTL for its CPU, predating the era of microprocessor chips. Additionally, TTL components were instrumental in the development of early personal computers, such as the DataPoint 2200, which served as the basis for the x86 instruction set. Furthermore, the integration of TTL circuits in computers like the Xerox Alto and 1981 Star workstations facilitated innovations like the graphical user interface. In terms of implementation, TTL gates typically featured a simple output stage or an open collector output for wired logic connections. To overcome limitations such as high output resistance in the simple output stage, TTL designs incorporated a totem pole output stage, enhancing performance with lower output resistance at logical 1. Despite its advantages, the totem pole output stage presented challenges like reduced voltage levels for logical 1 outputs. These design considerations shaped the evolution and widespread use of TTL technology across various applications and industries. Transistor-transistor logic operates as a current sinking system, necessitating current to be drawn from inputs to reduce them to a logic 0 voltage level. The driving phase must consume a maximum of 1.6 mTOR from a standard TTL input without allowing the voltage to exceed 0.4 volts. In the realm of TTL circuits, the output section of the most common gates is designed to operate effectively while powering up to 10 standard input stages, known as a fan-out of 10. TTL inputs are sometimes left unconnected to signify a logical 1, although this practice is discouraged. These circuits are standardized to function with a 5-volt power supply. A TTL input signal is classified as low when ranging between 0 volts and 0.8 volts in relation to the ground terminal, and high when between 2 volts and VCC, 5 volts. If a signal between 0.8 volts and 2.0 volts is supplied to a TTL gate input, the gate's response is deemed uncertain due to varying precise logic levels among subtypes and with temperature fluctuations. Outputs of TTL gates generally stay within 0.0 volts to 0.4 volts for a low state, and between 2.4 volts and VCC for a high state, providing a minimum of 0.4 volts of noise immunity. The highly standardized TTL levels enable diverse TTL chips from various manufacturers to be seamlessly integrated into complex circuit boards, ensuring compatibility even when employing chips produced by different companies. The 0.4 volts noise margins are deemed sufficient due to the low output impedance of the driver stage, demanding substantial noise power to drive an input into an undefined range. Depending on specific requirements, modifications can be made to TTL output stages, like increasing the voltage level of an output logical 1 towards VCC by incorporating an external resistor. This adjustment alters the intricate totem pole output into a simplified stage with notable output resistance when driving at a high level based on the external resistor. In terms of packaging, commercial TTL devices from the era of 1963-1990 are commonly housed in dual inline packages featuring 14 to 24 pins, suitable for through-hole or socket mounting. Military-grade components utilized ceramic packages for operation in extreme temperatures, while commercial temperature range parts were often enclosed in epoxy plastic packages. For aerospace applications, flat packs were employed, a type of surface mount package with leads conducive to welding or soldering onto printed circuit boards. Presently, TTL-compatible devices are accessible in surface mount packages, offering a wider variety than traditional through-hole packages. Due to its design, TTL is highly compatible with bipolar integrated circuits, as incorporating extra inputs to a gate only necessitates additional emitters on a shared base region of the input transistor, minimizing additional area consumption. Notably, IBM fabricated its flip-chip integrated circuits with TTL, mounting these chips on ceramic multi-chip modules. TTL devices consume more power at rest compared to CMOS devices, but their power consumption does not spike with clock speed as drastically as CMOS devices. In contrast to ECL circuits, TTL circuits use less power, have simpler design rules, but are notably slower. Combining ECL and TTL devices in a system can provide optimal performance and cost-effectiveness. However, level-shifting components are necessary between the two logic families. TTL is less vulnerable to damage from electrostatic discharge than early CMOS devices. Due to the output structure of TTL devices, the output impedance differs between the high and low states, rendering them inadequate for driving transmission lines. To address this issue, buffering the outputs with specialized line driver devices is common for transmitting signals through cables. ECL, with its symmetric low-impedance output structure, does not encounter this problem. The TTL totem pole output structure may experience a momentary overlap when both upper and lower transistors are conducting, leading to a significant current surge from the power supply. These surges can inadvertently interfere among multiple integrated circuit packages, diminishing noise margin and overall performance. TTL systems typically incorporate a decoupling capacitor for every one or two IC packages to prevent a current surge from one TTL chip from momentarily reducing the supply voltage to another. Since the mid-1980s, several manufacturers have produced CMOS logic equivalents with TTL-compatible input and output levels, often bearing similar part numbers to the equivalent TTL component and sharing the same pin configuration. For instance, the 74HCTT00 series offers numerous drop-in replacements for bipolar 7400 series parts, utilizing CMOS technology, wherein the T in HCT signifies TTL compatible. Moreover, successive generations of technology have introduced compatible parts with enhanced power consumption or switching speed. Although vendors promoted these various product lines as TTL with Schottky diodes, certain underlying circuits, such as those employed in the LS family, could be more accurately classified as DTL. Diverse variations and successors to the fundamental TTL family, which typically possess a gate propagation delay of 10 ennies and a power dissipation of 10 millidollars per gate, include low-power TTL, sacrificing switching speed for reduced power consumption, and now largely succeeded by CMOS logic. High-speed TTL, H, offering faster switching than standard TTL, but with significantly higher power dissipation. And Schottky TTL, introduced in 1969, leveraging Schottky diode clamps at gate inputs to enhance switching time by eliminating charge storage. Low-power Schottky, TTL, LS, merged the higher resistance values of low-power TTL with Schottky diodes to achieve a balance between speed and power consumption. Fast, F, and advanced Schottky, AS variants of LS from Fairchild and TI featured Miller-Killer circuits to hasten the low-to-high transition, yielding the lowest PDPs of all TTL families. Additionally, low-voltage TTL, LVTTL, was developed for 3.3-volt power supplies and memory interfacing, supporting a voltage level compatible with LVIC-MOS. Manufacturers typically offer commercial and extended temperature ranges, with specialized high-reliability parts catering to military and aerospace applications. Radiation-hardened devices, such as those from the SNJ-54 series, are tailored for space missions. Before the rise of VLSI devices, TTL integrated circuits served as the go-to technology for building processors in mid-range mainframe computers like the DEC VAX and Data General Eclipse. Some systems relied on custom components such as Fairchild CTL, while high-performance mainframes and supercomputers utilized emitter-coupled logic. TTL chips found their way into various equipment like numerical control systems for machine tools, printers, and video terminals. As microprocessors evolved, the role of TTL shifted towards handling glue logic tasks such as address decoding and bus driving, which link different functions within VLSI components. One notable modern instance of TTL-based design is the Gigatron TTL processor introduced in 2018. Despite being originally intended for digital logic signals, a TTL inverter can be configured as an analog amplifier by introducing a resistor for negative feedback. This setup can aid in converting analog signals to digital, although it's not typically used for primary analog amplification purposes. TTL inverters are also employed in crystal oscillators for their amplification capabilities. However, if a TTL gate receives a slowly transitioning input within the voltage range of 0.8 volts to 2 volts, it might unintentionally act as an analog amplifier, leading to erratic behavior in the output and increased power usage. Specialized TTL components with Schmitt trigger inputs exist to reliably convert analog inputs to digital signals, effectively behaving like a 1-bit A to D converter. In the realm of serial communication, TTL serial involves single-ended data transmission using transistor voltage levels to represent binary values, low for 0 and high for 1. UART communication over TTL serial is a standard interface used for debugging in embedded systems. Devices like graphing calculators, GPS receivers, and fish finders commonly employ UART communication with TTL. While TTL serial lacks strict electrical standards, driver-receiver modules like the MAX232 facilitate interfacing TTL with longer-range serial protocols such as RS232. Differential TTL takes TTL serial over a differential pair with complementary levels, offering improved noise immunity. TTL levels are also utilized in standards like RS422, RS485, and CCTalk for various signaling applications.